Hello, and thank you. I thought I might start my presentation with kind of give you a background as to what is a material scientist and what makes us different from everyone else. Material science fits neatly in between the studies of physics and chemistry and also engineering. We're the sorts of people who can help you find the right material for a thinner or stronger iPod screen. We can help you find a lighter, stronger, and more fuel-efficient nose cone for a plane. And we can also help you perhaps find a material that's better than this for the next generation of water bottle. But the way that we think is slightly different from you, because what we do is we think in terms of atoms, in terms of structure. So whenever we see a surface of a material, we don't think about just what the surface looks like, but we think about what's actually underneath. And I like to use the analogy of the matrix as a way of explaining this. Those who are not initiated in the matrix, whenever looking at a computer screen, looking at it, will see this series of green symbols. All you see is surface. But after you spend a lot of time in material science and looking at the atom structure and also the way materials behave, you start to see through that really into the real structure and what's actually behind the matrix. So you start to understand materials in a very different way. Whereas you may see carpet or wall, we start understanding the fibers that are made out of the carpet, what goes underneath that, what happens in those fibers in order to make them look red, to have their sort of fluffiness. We understand how the material actually ends up making the product look like it does. So my job is really to help my clients, who tend to be from all different industries, to find innovative material solutions, find lighter, faster, stronger, and cheaper materials that also look good. That has been my job for the last 10 years. Though I would like to say in the last 5 years, 6 years, that question changed. It stopped being lighter, faster, stronger, cheaper, and pretty, and became lighter, faster, stronger, cheaper, pretty, and also sustainable. And I think this gives us an understanding of what I call that there is no longer an independent material choice. Any material you choose, any material you choose to use in a particular product, that will have consequences that will have ramifications later on. So if we look at any material's choice, obviously it needs to appeal to a consumer. It needs to be culturally relevant. You don't want a product that's sold in the US may have very different ramifications if it's sold in China. Of course, design is a very important aspect of what we do. But then also sustainability adds in a degree of complexity that means you now have to think about the entire life cycle of that product. The simple one, of course, as everyone's seen, is paper versus plastic. You would have thought a simple choice. Surely we have enough information to decide which should be the right choice. But whether it's plastic bags, or in this case, whether it's a more updated version, which is a plastic bottle or a paper bottle, it's not a simple choice. And the people who made this had to think long and hard about this choice of material. I actually believe the person who designed and created this is actually in the audience. So it's not a simple decision. I'm sure they'll tell you that when you're coming to sustainability, the simple choice of which materials to use becomes very complex. So what I'd like to talk to you about now is how we take that material knowledge and that experience and help our clients. Puma came to us a few years ago and said, we want to redesign the shoebox. We want basically a more sustainable product. So in the way that we do, we took the best minds at Puma, the marketing and sustainability people, we put them together with Fuse Project, a San Francisco-based industrial design company. We also put them together with the people who quantify sustainability, PE International in this case. We put them together, and basically that team tried to develop the new shoebox. It's hard to redesign a shoebox. It's been engineered to death. It's cheap, it's lightweight, it uses very little materials. And when we first approached this, we thought, okay, well, we need to use more sustainable materials, so let's use pulp paper. However, by doing this, and we went back to Puma and said, look, we've got this new design, it's a great idea. We did the analysis, the sustainability analysis, and it came out that this product it was a little better, wasn't good enough. So Puma, to their credit, said, not good enough, let us try again, let us see what else you can come up with. And we realized that the best solution ended up being not a box at all, but actually a bag. The bag is the thing that you basically put the shoes in once they're manufactured, and that becomes a thing that protects them all the way through to the consumer, and then the consumer takes that bag home. So that basically negates any need for a box. So the box just becomes structure, and we actually made savings of about $3 million a year just in cardboard. So the reduction in cardboard costs was significant simply by saying that, yes, in trying to redesign a shoebox, you really don't need a box at all. You just need something which can carry that shoe all the way through its life. And of course, Puma customers being the way they are, they found creative ways of reusing that bag. So this sort of breakthrough innovation is a great example of how sustainability thinking and thinking about the entire life cycle of a product can change into breakthrough innovation which gives cost savings as well as those sustainability advantages. Quick note about the sustainability of that box. We actually shown that we saved about 1 million litres of water, about 1 million litres of diesel fuel, and about 500,000 litres of fuel oil simply by changing from a simple box to this bag. So where else can we find ideas for breakthrough innovation? Well, in the work that we do, we deal with a range of clients that come from automotive to architecture, fashion, sportswear, interior design, product design. And we feel that they all have a lot to learn from each other. This sort of cross-pollination, where it's possible to source ideas and technologies from different industries, I think has a great way of solving a lot of our material problems. We do this through our work with our clients, but also it just so happens that we also run and curate the world's largest innovative materials library. It's housed in New York. We have 8 other locations. You will see tabula of this kind over in the lab. And what it's done is it's allowed us to understand fully the full range of materials that are available to our clients. And this helps them in sourcing ideas from different industries. Yes, this is a great resource. Yes, we use this every day for sourcing materials for our clients. But where I think it has the greatest value is when they can take an idea from a different industry, where it's been tested, where the context of that material has been understood, and maybe adapt it to their own. Every material that we show is commercially available, so it's made its way into the marketplace. So you can understand that it has the materials used have some value, and if it's commercially successful, then it works in that industry. How can we then perhaps adapt it to another? I want to give you a couple of examples of effective cross-pollination. My first one is, let's imagine you had a golf club. If you want, the whole idea of a golf club is you want it to hit a ball as hard and fast as possible. Well, what other industry has that same problem? Well, it just so happens that missiles that are used in war have the same issue. They need to be able to hit the tank as fast and as hard as possible. So the material used in these type of tank-busting missiles, the material actually there is very effective when put on the end of a golf club. You end up being able to hit golf balls a lot harder and faster than before. So that technology transfer, you take the idea of a solution in one industry and then adapt it to another. A second is maybe not just a material, but a process. Sailing for many years has tried to create the best possible strength and ability to capture wind with the least possible weight. And they've realized that the best way to do that is to create lines of strength only where they need it. So in the image on the right-hand side, you'll see this sail, but the lines there are actually embroidered in lines which give incredible strength only in those directions. That then can be used as a way of creating the lightest and the fastest running sneakers, where all you need are lines of strength in particular areas. So adapt the idea of lines of strength from sailcloth, and then you can adapt it then into a running sneaker. So we can look at industry, we can look at the way that solves problems, but I think I'd also like to look elsewhere, and we do that by looking outside of industry, and what we found is that a lot of our forward-thinking clients and designers are using nature as a blueprint. Nature has a great way of solving problems. Anything that's in nature today is only there because it's been through 1 million iterations, and every other iteration died. So nature has a great way of weeding out some of the weaker of the solutions. So if we look to nature, the idea of biomimicry, of mimicking nature, is a great idea. Example here is actually the 3rd generation of fast skin swimsuit by Speedo, where they used the idea of shark skin as a way to make the swimmer move faster through the water. So what they did was they took the surface and they tried to mimic the surface of a shark, and they ended up with, admittedly, the fastest swimsuit that's ever been designed. But here I think is where the interesting point about biomimicry. They tried to take a synthetic material and replicate a natural material. But what you find is that nature is way more complex than we give it credit for. This is actually the surface of shark skin. It would be virtually impossible using current techniques to actually develop a skin that looks as complex as that. But that's what the shark skin looks like. So in our attempts to achieve biomimicry, our problem is that we're pretty clumsy at it. So I suggest that instead of doing it that way, going from industrial material and trying to mimic a natural material, the next generation of materials are actually doing kind of the opposite. They're saying, okay, well, rather than fighting against nature and trying to mimic it, why not use it? So I've got a good couple of examples here. The first one is a jacket that's been produced with a material that was actually grown in a bath. Suzanne Lee, who is the head of a company called BioCouture, grows fabric in a big iron bath, sugary tea and bacteria. Those two things. The bacteria love the sugary tea, they eat it up, and they deposit this fabric, in this case can be sewn into jackets. There, instead of using a synthetic material and trying to mimic the natural process, you say, okay, let's work with the natural process in order to come up with a solution. I think that's a great example of how instead of working against nature, we can actually work with it. A second example is material that's currently being used for two different applications. First one is insulation inside walls. The second is packaging. This is a material that grows in the dark in 7 days. It's mushrooms that just so happen to have very similar properties to expanded polystyrene. So we use expanded polystyrene in insulation and also packaging. The mushroom can do exactly the same thing. But the advantage with the mushroom is that you require no energy. All you do is basically get a big factory floor, get a whole lot of agricultural waste, rice hulls, wheat chaff, whatever, lay it down on the floor, and then spray with a big industrial hose this material called mycelium onto the surface. You spray it on there, so you've got this big, almost football field-sized patch of sprayed mushroom. It's in the dark, no lights, no heat. You just leave it there. 7 days later, you end up with materials that look like that, that have the same sorts of compression properties as expanded polystyrene. Dell is currently prototyping this because what you can do, you can mold it into particular shapes. So it's prototyping having its basement, which it wasn't really using for anything, having that as the floor on which it grows the packaging material. That packaging material is then brought upstairs to where they're actually making the computers, and then it's just used to pack the material and it gets shipped out. So working with nature allows us to create solutions that require very little energy, almost zero waste, and ultimately at the end of their life are able to be biodegradable or compostable. My last area in terms of thinking about nature is the area of 3D printing. Now, those of you who have been to the lab will have seen some examples of this, which is simply just an alternative way of manufacturing. Here you can see this is a complex shape that's being molded. But this, I think, actually is a great idea from nature in that instead of heating and treating and then forcing synthetic materials into particular shapes, as we normally do with injection molding, this uses the simple idea of growth. 3D printing is a simple growth process, and it allowed us to grow objects which are way more complex than you can really imagine. So it's possible now to grow complex products or parts that have moving parts that are made out of different materials. And this, I think, shows a great example of how it's possible to use the way that nature treats things and the way it grows, but in a mechanical way. So the idea of biomimicry and the idea of actually using nature as a positive force, I think, has great value. And I feel that as we head into this 21st century, if one thinks about the 20th century, we can consider that very much a synthetic century. We used all of our powers, all our chemists and our physicists and our engineers spent all their time trying to make synthetic materials that were as good as natural materials. I think as we move through the 21st century, I think we will understand that we have a lot more to learn from nature, and that nature will come up with a great number of surprises and will actually prove to us that it can probably make stuff cheaper, I think more efficient, with less waste than we've ever been able to do using synthetic processes. So, in conclusion, I think what I like to say is that my work as a material scientist has been spent using science to try and help my clients solve their material problems. I spent a lifetime using science and trying to have it as a way to solve some of our most basic material needs. And in my life, although I am trained as a scientist, though, I find that most of my friends, most of the people I really interact with and really enjoy the company of, tend not to be scientists, but actually creative people. Most of my friends tend to be photographers or artists. They tend to be sculptors, designers. And I think it is that combination which is the most important. I get my energy and passion from those who can imagine the future, who aren't perhaps constrained by my knowledge of materials. They imagine the future. And I think a great example of that is if you actually take 3D printing. 3D printing has been a process that engineers have had for the last probably 20 years. And they spent all their time refining it and making prototypes. It was a rapid prototyping process. So engineers take a technology and they refine it and make it better, and it's better at doing what it's supposed to do. But you put that process into the hands of a designer, and they suddenly create beautiful things. And from that, it was around the year 2000, from that, once designers get their hands on it, once artists start using 3D printing, they can create things of beauty, and suddenly you can really see what's possible with this sort of manufacturing process. So in closing, I'd just like to say that although I think science is an essential part of what we do, I think if we are to think about a sustainable and better future, I think what we need to do is we need to put those ideas in the hands of creatives. Let them imagine the future, and then let us, the material scientists, then try and solve that problem with using materials. Thank you very much.